Hello, everybody. Welcome back to another edition of Water Talks. I'm happy to be joined by Stephen from Freese Nichols today, when we're going to go through some ICM modeling, and in particular, kind of inside the fence, working with ICM at wastewater treatment plants in kind of a unique way of using ICM that I thought was really cool and definitely worth sharing with you all out there. All right, so and kind of presenters today, you've got myself, Tim Medeiros, an SE here at InfoWorks. Been with InfoWorks for about 4.5, 5 years now. Been hosting these water talks now for almost a year now, since about last April. Again, just going through different topics, all things water related. I've been within the asset management space mostly here with InfoWorks, worked with different utilities and clients all around the country, all around the world, in fact. But really happy to be talking some wastewater modeling here with Stephen today. Stephen, do you want to go ahead and introduce yourself real quick here?
Yeah, thanks, Tim. Hey, everyone, name's Stephen Rhodes. Like Tim mentioned, I work with Freese Nichols in our asset management modeling group. Been working with them for about 13 years now, graduated from University of Texas at Arlington, and have been pretty much using InfoWorks software for the duration of that period, and have really gotten into CS long ago and seen it transition to ICM. So anyway, excited to talk about this. I think it's an interesting little feature that is unique to ICM. You don't get to do this in really any other software package.
Perfect. Yeah, I know definitely in support. I remember going back and forth with you, just years ago in different software. But yeah, great to have you on today for sure, Stephen. Thanks for taking the time.
Yeah, thanks for having me. Want me to jump in?
Go through a little bit more background for folks on here. If you're new to Water Talks, again, kind of the intention of InfoWorks doing these has been to kind of flip the webinar around a little bit. If you have questions, for Stephen, please enter them into the little questions portal there in GoToWebinar. Stephen's got some great slides that we want to make sure to get through. I think there are about 20 of them or so. But yeah, we are certainly here to answer those questions and have that be a little bit more the focus of our Water Talks presentations compared to just a normal standard webinar. And just a little preview for you next week. Again, we'll be back Tuesday, same time, and we'll be flipping back over to the water distribution side. We've got another guest presenter coming in and talking about a little bit on fire flow. All right. Well, with that, yeah, Stephen, floor is yours. Thank you.
All right.
Oh, let me share my, let me change my presenter to you there.
Yeah.
There you go.
All right, can you see the presentation?
Yep, I have to skip the first few. There you go.
Yeah. Good deal. Well, appreciate everyone tuning in and glad to be here and talking about this particular subject. Like I said, it's an interesting one that you'll find a presentation every once in a while at WebTech or Web Collection Systems about where someone has used ICM to do treatment plant modeling or really in-depth hydraulic assessment for some type of treatment process or big lift station, but it doesn't come around very often. And so anyway, talking with Tim, thought it would be a good time to at least put this out there and just kind of show how we've at Freese Nichols have used ICM in particular to do this. So just a quick agenda here. You wanted to talk through some implementation considerations. ICM is the software package, is kind of another tool in your toolbox, if you will, and so it has a place of where it should be deployed and maybe where other things should be considered, and we'll get into that. Also want to talk briefly about model development calibration. There's a lot of documentation out there about how to really go about doing that, so I won't spend a ton of time on it, just more touching on kind of like some of the highlights and maybe key things to consider. And then we'll get into real-time controls. Most of the time, these treatment plants are other things you might use ICM for to help with design. There's real specific controls to those facilities or processes. So real-time controls must be developed to kind of mimic that if you're going to do kind of extended period runs. And then lastly, I'll get into some different use cases where we've kind of applied the ICM software package to help us with design of either treatment plant components or storage or some other items. So let's just jump right in. So as I was saying, ICM doesn't necessarily replace any of the tools you might have as an engineer, but it is another tool in the toolbox. You have, I've got 4 here, but there's probably more. Oftentimes we'll do hydraulic design with a spreadsheet of some sort. There's also more sophisticated stuff like CFD modeling, or even like this far right image shows physical scale modeling. And so, where you want to deploy these different technologies might depend on how complex the design is and how much risk in the design you're looking to mitigate. And so what I've seen is that ICM can be a good alternative to a spreadsheet when you have a kind of a more complex hydraulic situation occurring at a treatment plant. So, larger plants a lot of times will have like a smaller, older plant and then a larger new plant, and there's a lot of parallel piping and flow splits that occur when you do that. And that can get difficult to accurately track in a spreadsheet. Not to say that it can't be done, but it certainly gets a little more difficult. And at some treatment plants, they might be, the gravity collection system might go all the way through primary clarification. And so what happens at the treatment plant has a direct impact to the collection system. There's not necessarily that big influent lift station up front that's maintaining a steady wet well level that the collection system sees as its downstream HGL. Instead, there's all these treatment processes that are kind of setting that. And so that HGL can vary as flows increase through the plant. And some other topics here, if you're trying to do a more extended simulation, understand how varying flows move through the plant or the design, ICM can help with that. And then obviously, visualization of the results. Spreadsheets are great. You get the numbers you want, but it might be a little bit more challenging to see it or to understand what the results are. And so, obviously you can do something like CFD modeling, like that. The third graphic kind of shows that really kind of highlights what's happening. It's a really nice visual. Obviously there's a price to be paid for CFD modeling in some cases, and you may not want to deploy it everywhere, only in just really complex hydraulic situations. So ICM can be that good balance there between it. Thinking about CFD modeling, ICM wouldn't necessarily replace that in any way. ICM is not going to give you really good hydraulic representation of like a big vortex drop structure or something like that. That you might still want to push that to CFD modeling, but more higher level, simpler modeling hydraulic situations, ICM can be a good solution for. So we'll just jump into model development. This just kind of shows a plant and the various treatment components kind of outlined in gray. And on the right, we have what that looks like in the hydraulic model within the ICM software package. And so basically, you've got to go through a process of either pulling as-built plans or doing survey on all the critical elevations, vertical elevations, to help fill out that model, defining the channel widths and depths. This is an example of a clarifier, understanding how deep the center of the clarifier is, what the sidewall depths are, weir elevations. ICM has a lot of options for weirs, and so you can easily model a V-notched weir. You just have to kind of define the length and the number of notches and the spacing, and all that information either can come out of as-built plans or you can go have it surveyed. Volume representation is always kind of a big deal when you're doing this in ICM. The model will create, I guess, volume, I should say, in different places, and one of those is the junctions of 2 channels. In reality, there's not really anything there, but in the model, you might have the need to have a junction there to account for like a change in elevation or something. And so you can do break nodes, but those are mainly used for pressure pipe, and the model will throw a warning. So what we've done is just typically represent those as a sealed manhole with an area of 1 square foot. and that kind of minimizes that excess volume that's being represented in the model. Another thing to kind of keep in mind as you're building these is that you'll have to do something to define minor losses due to bins and T's and that kind of thing. ICM has an inference tool that'll develop head loss or define a head loss parameter based on the bends or angles of the pipes coming in and out of a manhole, but it's not like a typical like minor loss K value. It kind of runs on its own separate equation that was developed by Wallingford back some time ago. So you don't necessarily want to use that. You want to use define minor head losses and coefficients for your bins and T's. This is just an example of what that clarifier looks like after you pulled the data either out of survey or out of as-built plans. You can have kind of as many or as few of these weir links as you'd like. They just basically help you represent the flow passing over that weir into that effluent channel. So if you want to have better understanding of the depth of flow in that channel, you can have more weirs. If that's not important, you can just have one weir that passes over, but you won't have a really good idea of what the depth of flow looks like across that entire channel. You use a storage node to represent the basin of the clarifier itself, kind of shown in the bottom right. And then, as I said earlier, you'll calculate out your weir length based on either surveying or as-built plans and define all that information in a V-notch weir definition. It's also important to note, you'll have RAS pump features that you'll have to insert in and have, that return flow from the clarifier to the aeration basins. And, you can oftentimes get the pump curve information from the operators or get some sort of information from them about how they typically operate the RAS pump system, and that's where your real-time controls can come into play there, just to make sure you're mimicking that return activated sludge operation properly. So then, kind of just briefly jumping into calibration. In the past, we used to have a surveyor go out, and this was years ago, but we'd have a surveyor go out and he'd record the time, and he would take a water surface elevation measurement at all the different structures, and so he would just kind of move through the plant recording time and water surface elevation, and that worked okay, but it was just kind of one static point that kind of varied really, because it might take him an hour to get all the way through the plant. Now what we've done is utilize the ADS echo units. They're just a level only sensor that can be I guess it's a down-looking sensor. It can be mounted kind of on anything. They can really get it to fit just about anywhere. And so we've started deploying these kind of across, the entire HGL profile, if you will, of a plant, just at the end of every process, so that we can really get a good understanding of what maybe the true HGL is of the facility, and then use that information to calibrate those minor losses and things of the ICM hydraulic model. And so these are just some examples of just showing model versus observed at different process locations within a treatment plant. I won't dig too far into real-time controls in this. There is a really cool document that I found years ago at a user group, I guess back in 2013, what this says, that Irene, she did a presentation that really documented just how the RTCs work, some tips and tricks on how to use them. It's still kind of my go-to document anytime I get into RTCs. Unlike riding the bike, you do forget if you don't use them very often. So I find myself going back to this just to kind of recall some of the functionality of those things, or how to get the statements to work right at times. But in general, what you want to do while you're putting these together is just think in terms of if, this, then, and be really clear about what you're wanting it to do, and thinking through if how you're setting up the rules is going to really do what you want it to do. And then always, when you're kind of QCing these, trying to figure out if they're working or not, you can graph the RTC controller status and whatever conditional element you're using to drive that controller, and help you see, okay, did the condition happen, and what did the status of my controller do? And if you're seeing the two correlate as you want it to, you know you're on the right path, or that you got the RTC correct. If you don't, then you know something's not quite translating, and you might have to kind of troubleshoot into that further. This is one of the use cases we've have used these models for. It's just a simple hydraulic assessment, you know, not taking into account any process or solids, just hydraulic. How much flow can we push through the plant? And so for this particular use case, we did an average day flow scenario, peak 2 hour, and a 4 peaking factor, just to kind of see how the plant would perform. And got some really great feedback from the client. They've had a 4 peaking factor pass through the plant and had trouble. They were kind of surprised at how well the model kind of highlighted specifically in like the effluent channels, where they were starting to see those channels get really full, and those effluent weirs beginning to overtop. So it was, I think it can work really well for this, especially if you have, you know, good level data for dry and wet weather that you can kind of calibrate those minor losses to. Another use case here is just as a design aid. This is a treatment plant in North Texas. Flow enters the plant from 2 directions. Gravity is through screens and primary clarifiers before being pumped into the plant. So any improvements that are made kind of in that screening or primary clarification process of the plant have direct impacts on the collection system. And so before, you know, any improvements can be made in those areas, like you may want to understand what those do to your collection system. And so in this instance, the plant was looking at adding grit removal in, and so of course that's going to add so much additional head loss into that profile between the clarifiers and the headworks, and that is just going to translate into a higher HGL in the collection system. So we used ICM to not only model the water surface elevations within the plant with the addition of the grit removal, but we also used it with the collection system and see how, if we raise this HGL as a result of this grit removal facility going in, you know, what's that do to the plant? What's that do to the collection system? And so it's just kind of an example of, you know, what that looked like within the plant. We just had some simple mapping, just calling out, you know, no grit existing scenario conditions with a grit option or alternative in service. And really what we were trying to figure out in this instance was, could you maintain gravity flow from the collection system, one branch of the collection system, or were you going to need a lift station because the HGL as a result of the grit removal was going to be too high, and the collection system was going to have the potential for spills during wet weather events. And so we looked at a couple alternatives. This is just a few. So this first alternative was the gravity option of just trying to fit the grit removal into the existing hydraulic profile of the plant and continuing the gravity operation. And what we found is this particular portion of the collection system, the ground elevations were kind of low, and so that additional head loss occurring because of the grit removal and all the bends of the pipes and that kind of thing, it's still, the model indicated there could be, you know, SSOs just immediately upstream of the plant. So a second alternative was installing a lift station, like a lot of plants have, a big, you know, a sizable influent lift station that maintains kind of more constant wet well elevation. And so with that option, you know, obviously we didn't see any collection system impacts because we're able to draw down that level and maintain a consistent downstream water surface elevation for the collection system. So as we were doing all this, some interesting things kind of came about. You know, we put the grit removal facility in the model using the user head loss links to represent the grit removal units themselves. Each unit had like a foot of head loss, and so it was really easy just to use those user-defined links to model those in ICM. One of the advantages we found with ICM is it's a good way to visualize, in this case, velocity. And so a lot of times, you'll check specifically for grit removal, you want to maintain, 2 feet or higher per second velocities in the influent channels of the grit removal facility, so that you're getting all that grit to the grit units themselves. And so what we're able to do with ICM is kind of visualize and run a varying flow pattern through the model, so we could see, okay, at peak flow of 384, which is our design peak, how are the velocities in our influent channels? And they're generally all green, so we're getting 2.5 feet per second or so. Well, what if we look at 255 NGD of flow? What does that look like? Or 166, which is the permitted capacity. How are we looking on a more typical permitted capacity standpoint? So really easy way to kind of see how the velocities might vary in different flow conditions, and what parts of the channels might be experiencing lower velocities or higher velocities. And what was good about this is the design team was able to come back and look at the geometry of those channels and kind of decide if there was ways to adjust those to keep the velocities up. They also ended up developing an operational strategy to close off these first two grit removal channels, so that flow wasn't passing through those, and you had more flow, more velocity in that channel as a result. So it helped them kind of see where we might need to make some operational changes, or make operational changes, but define some operational strategies to help maintain adequate velocities. This next one is just an example of storage. A lot of treatment plants will have offline storage basins to help manage peak wet weather flows. And this is just an example of where we've used ICM to kind of model those facilities. They're usually very straightforward. You might have a diversion structure with a weir, and then individual basins you can model as a storage node again, and then in this particular case, as one basin filled, it spilled over into others, and so you'd have just that overflow weir to move the flow across, and then your drainage lines leading to a pump station that pumps the flow back to the system once the peak event is passed. I think this is just kind of a close-up. So one of the challenges with storage facilities that maybe you should be aware of is that during initialization, if you have all these gates closed so that they would fill during initialization, these storage nodes will fill. And so when the run actually starts, they'll be somewhat full of flow already, and it could be pretty substantial. It could be half or more full of flow. So then when your peak event comes, everything overflows. And so the solution is to have an RTC on a dummy gate and a dummy outfall, and keep all these gates open in your RTC. And then your first rule, and I probably have some more language here in a minute, the first rule is basically close these gates. So what that means is during initialization, these gates are open, that flow can pass through, the model can get through initialization without too many headaches. Then when the simulation actually starts, that first rule, the RTC, is applied, all the gates close. And then once the diversion occurs, these things will begin filling as needed. Yeah, and so this just kind of summarizes that. So if you have your initial for your gates, so there's a rule or an RTC for each of those drain gates, and if your initial is set to a value, that is the value that'll be held during initialization of the model. And then if you define a rule, just a default rule right off the bat that sets it, that basically closes the gate, when the simulation starts, that gate will close the first timestamp, and then you no longer have to worry about flow kind of passing through. So there's kind of some of those nuances to RTCs, and that kind of come into play when you do these types of facilities. in this case, once we actually had these controls in place, we were actually able to do a really long run of 10 years of historical rainfall data to better understand just how often would this storage facility wet out. And there's definitely a lot of different ways to do that kind of analysis. This was just one that we did. We just loaded all the data in there, put it on a pretty beefy VM machine and let it run. And so it was kind of a low effort on our part just to let it go. But basically what it kind of told us was that, you know, they might see 1 or 2 events where this thing would activate, reach its full capacity. And so really helpful analysis just to kind of be able to see that. So it was one of those things, as we developed the model to verify the hydraulics of the design, we kind of started seeing these other abilities that doing this in ICM allowed us to have. And like I said, there's a lot of ways to do this. You don't necessarily need ICM to do this, but it can do it, and it creates some really useful graphics when it does. One thing to be aware of, if you do those long extended runs for multiple years, it can eat up a lot of processor power and take some time. And then the simulation files can be quite big, so just be aware when you go to set one of those things up, if you're not going to do anything to kind of prune down the rainfall data or anything like that, it's going to generate some really large results. All right, I ran through that kind of quick, but I wanted to leave a bit of time open for questions. Tim said these are usually kind of a back and forth dialogue, so hopefully that gives folks some time.
Yeah, perfect. A lot of good stuff in there. Appreciate it, Stephen. Thanks. A couple of questions on that RTC presentation you mentioned. I was doing some digging myself, trying to find that presentation from 2013. And Irene, I know, was from our InfoWorks Australia team. So if you happen to have that document, you might be able to actually find it faster than I might, quite honestly. Okay.
Yeah, I can send it to you.
Okay, great. If you can send it to me, I can make sure folks that are interested can certainly have a look at that and be able to reference that. Perfect. I had a question about this is kind of wastewater treatment plant modeling. Were you able to connect this to the overall collection system model as well?
Yeah. So in that one example of the grit removal, we actually did that. We connected the treatment plant model to the collection system just to get that direct connection and make sure there was no, I guess, misunderstanding, for lack of a better word, of what that downstream HGL was for the collection system. Really be aware of how much of a treatment plant model you need and how, I guess, how many RTCs you got to have to support that, because it, in that particular case, we actually have a full treatment plant model, and the RTCs, there's a lot of RTCs to control all the different processes and stuff, how flow splits between aeration basins and that kind of thing. And it has to have a really small timestamp, simulation stamp to run. And so if you take that kind of level of detail or that model and apply it to a collection system where you're running on a 5-second simulation timestamp, it could take hours to run potentially, depending on the size of the collection system. So when you connect those two things, just be really aware so you can kind of optimize that runtime, how long that simulation is going to go for. In that particular case, we got rid of all that stuff because once the flow hit those pump stations, it pumped up into the aeration basins, and so those pump stations set the wet well elevation. We didn't need the rest of it, so that allowed us to simplify the model, reduce the RTCs, and we could have a larger timestamp so the model ran faster.
Awesome. That was a question from, I think, a former Freese Nichols, Doug, saying hi.
Oh, yeah.
Asking about that. A couple other questions kind of coming in here. One, our own kind of InfoWorks zone, Bob Dickinson, I imagine you've probably spoken to a time or two,
Oh
kind of
yeah.
noted, he tried doing something similar like this with Swim 5 engine, but obviously there's some definite difference there between the ICM sim engine and Swim 5's. I guess I'll pose that question to you. Have you or anyone at Freese Nichols, do you know, tried to do something similar with kind of a swim engine, or kind of what are the differences you notice there between, doing some of this, wastewater treatment plant design and calculations with the sim engine versus the swim engine?
Right. Most of the time, we've almost always done this in ICM. We did a treatment plant model one time with your competitors, Bentley with sewer gyms, and it was very difficult to do. It just doesn't handle pressurized gravity flow situations the same, and so I think we got to a solution, but it was much different than the implementation was much different than maybe with ICM. I've seen some presentations where they've used EPA Swim to do it, but I haven't had any direct experience with it personally.
Okay, yeah, some additional kind of questions coming in here from David. Speaking of time steps, what results TS did you use to analyze the model output? I don't know if you can see that one in the questions portal. Yeah.
We probably did it the old-fashioned way and just pulled out what we needed and dumped it into Excel to graph or to do like that. But I think that's definitely an option. We didn't even get into the time series database stuff, but there's a whole lot of functionality that can be added and all that.
Yeah, it was definitely the whole time series database you can kind of add to ICM. I know Nathan's done some presentations from Innovize on how you can kind of add that and bring in that real-time data. Let's see, from Jamil, how much of an added value is it to model the plant if there is a hydraulic break, a lift station at the end of the collection system?
Right. So then in that case, if you have an influent lift station that's holding a steady wet well elevation, the impacts of the plant on the collection system, might be minimal as long as that lift station can maintain that level in all scenarios. And you wouldn't necessarily need a treatment plant model to tell you what that looks like if it can't. In that case, the treatment plant model could be of value if your plant has it's a more complex situation like I was describing. There's a lot of parallel pipes or flow splits that make it difficult to easily model with a spreadsheet. And if you want to kind of just see those kinds of results more spatially or graphically. But I think it definitely varies on what you're trying to do and what your situation looks like.
Perfect. From Spencer, another one here. Did you have any challenges in getting the model to initialize work? Some of the troubleshooting you did in that initial kind of model setup there?
Yeah, we did initially. So like that storage basin example, that one gave us a real hard time initially on initialization because we didn't really have that dummy gate system set up yet. And so it either wouldn't initialize or it would, and then we would get crazy model results because the basins were already half full, and then they would overflow. And so just kind of working through that logic, I think I got in touch with someone at Innovize on that one to help me understand just how you can define those RTCs so that those gates will be open during initialization and closed in the simulation. And I didn't realize that you could really do something like that, but it worked out well. In the larger plant model, we did have to work through initialization challenges. A lot of times it was just putting some definition on the initial values of the RTCs for like gates or orifices. You might represent butterfly valves as orifices, and so kind of setting some different values for that so that the model doesn't try and pick up something that's just really out of range and kind of throws off the flow balance of everything seemed to help. It can definitely be a challenge for sure, but Innovize support is usually very helpful in guiding you through just kind of what's worked for them and what hasn't when you start talking about pressurized pipe situations.
Sure that was Carolyn or Nikki or Bob or something like that.
Yeah.
Probably on the phone or something. One thing I did want to point out for everybody is Stephen did provide the slides for today in PDF format, so you can see those in kind of the handout section. I think it's beneath the questions in the chat, maybe in the GoToWebinar, so you can download those and kind of see what Stephen's again kind of referring to and talking about the storage basins and things like that. Kind of similar to that question, what factors did you primarily adjust during maybe calibration of the model? So maybe not so much controls, but things like roughness, minor losses, anything else like that?
Yeah, we went back and looked at minor losses, and then a big one is the discharge coefficients that are applied on sluice gates. Those can be those can have a big impact on how much head's generated across the sluice gate. And so looking at those and evaluating just what those values should be set at, you know, how much head is this sluice gate really generating if it's, you know, wall mounted and it's the full width or beyond of the channel. You know, it's not going to have as much impact if it's kind of in the channel proper. And so I think that was a big one that we really honed in on, or I've seen in the past us hone in on, is what head losses we're using on sluice gates. Everything else we generally keep kind of defaults. You know, there are the minor head losses for like entrance and exit losses that are probably more geared towards like large reservoirs or larger volumes than just like a pipe connecting to a manhole, or where your pipe is, you know, a 90-inch pipe connecting to a manhole. There's probably not going to be quite as much head loss through that because the manhole is usually built around, or at least in this case, the manhole is built either on top of the pipe or around it. So it's not really like it's hitting this static volume of water. It's just kind of continuing right through the structure. So sometimes those entrance and exit head loss values are a little excessive.
Yeah, sounds good. Couple questions here kind of on that 10-year simulation, which I know, folks internally, I was talking with, some other folks that are like, that is so impressive. You got 20 CPU cores, 10-year simulation. Like that's quite a big one there. But yeah, what were kind of the upstream and downstream boundary conditions applied during that kind of 10-year, super run, if you will?
Yeah, so we actually, I mean, for better or worse, we were just like, let's just see what it does. I don't know, and if it crashes or generates something big, then we'll do something different. But it's pretty low lift just to drop a bunch of rainfall data in there and hit run. And so on that one, it actually was a model of that entire collection system or basin of not the entire collection system, I guess you should say, the one basin of the collection system. So it had all its subcatchments and was just generating runoff, and the diversion structure was there and would activate once flows reached, the activation level. And so we just modeled the whole thing just to see what it would do. Like I said, there's definitely, I've seen a lot of different ways of doing that. But we just wanted to see how it would work and thought it would be interesting just to try.
Yeah, absolutely. That's awesome. Kind of similar to that, Evan kind of asked, is there a break point? I mean, you had 20 CPU cores and were able to kind of do that, but is there kind of a break point where trying to be too accurate and represent hydraulic elements will degrade the model performance? Thinking about the number of weirs on the clarifiers, and things like that. So I guess he's actually looking at kind of, the actual hydraulic elements. Not so much the time, maybe.
Yeah, we've done those clarifiers a little bit different with varying numbers of weirs. I don't know that I've ever seen too much of a performance hit. Just like with a lot of those, we'll just run on the standard laptop, or a smaller or a detuned VM machine with maybe 8 cores or 12 cores or something, and they all run super fast. I mean, those little plant models will run in a minute or something. So if there is a difference, it's not noticeable. More often than not, it causes trouble with initialization, and you kind of have to sort through that dynamic of it because it's trying to split the flows over too many things or something like that, and that might be where you run into trouble.
Mm-hmm. Yeah, no, I mean, part of what made this presentation I know really interesting to folks at Innovyze is we see ICM used all around the world, typically for really large scale systems because the simulation engine is so fast, and it doesn't matter if you've got 100 elements in there or kind of a million. Those simulations, for huge utilities, do run very quickly, with really high performance. So it's not so much typically that number of hydraulic elements that you need kind of that hydraulic power for. You needed, and again, correct me if I'm wrong here, Stephen, but those 20 CPU cores, that was for just the duration of the model you were running, a 10-year kind of simulation, not so much the number of elements that was really necessary for it all. But yeah.
Yeah, we started with just, I think our normal VM machines might have 8 cores or something, and so much memory. Well, we did a couple of tests just to see, how long is it going to take, and how much does ICM want, and does it want cores or does it want memory? And so we kind of fiddle with those. It doesn't seem to care too much about memory. It definitely will use cores. The more cores you give it, the more it'll use, and the faster the simulation will execute. I think we found like somewhere around 20 to 25 or something like that. It kind of just didn't have any more performance gains. It didn't really change the simulation runtime too much. I don't know if Innovyze has done stuff like that or has some thoughts on it, but that seemed to be kind of a good point in what maybe our like BT guys could handle as far as having some VM machine hogging up resources and a reasonable simulation time.
Yeah. Perfect. A couple questions here for Paul. First question, did you consider an initial state run to initialize and kind of simplify your RTC controls?
I honestly haven't. We almost went down that road when we were having trouble getting one of the models to initialize years ago, but we're able to kind of get it sorted and it worked out. But that is one option, I think, if you can't get the model to initialize. Those hot starts, as I've heard them referred to in the past, can help kind of bypass some of that and help you get to a simulation.
Gotcha. And then second question, have you tried running this model or any of the models with water quality parameters as well?
I haven't, no.
I
want to. I think that'd be kind of cool to do, just to see how that works out.
Yeah, next time. We did get an explanation from Bob here chiming in. Maybe that 20 cores you kind of hit at some point, it starts to slow down the simulation because there's so many cores, core-to-core communication, talking to each other, kind of thing. So maybe that's kind of the threshold 20 CPU cores you hit there. Another question kind of on those model boundary conditions you hit earlier. Hold on, let me double check here. Not repeating the same. Are model boundary conditions and rainfall data applied in 10-year simulation? Were those from observed data, or did you just kind of repeat the same pattern, or was that from observed data, I guess, that 10-year simulation?
Yeah, we pulled down, we talked to the folks at NOAA and got hourly data for a 10-year period at a rate gauge at an airport. And so it was definitely kind of a high level assessment. It wasn't, GAR data or multiple rain gauges or anything like that, but we were able to get that much data, at least for one gauge, and applied it kind of across the entire system. There wasn't a lot of sources, I guess, initially for that length of data to get more spatial resolution, I guess you could say.
Mm-hmm. Okay, good. And then questions coming in here. How do you deal with the base flow depth that makes the simulated water level higher in the channels? Did you have to deal with that at all? How did you deal with the base flow depth that makes the simulated water level higher in just the channels, I guess, than the pipes?
I mean, I would say, I guess when you're doing calibration, you're adjusting things to get to an observed water surface level and making those changes to make it match something that's been observed. So if the model's adding some amount of base flow during initialization, which is fairly minor usually, you're kind of taking that into account, I think, with the calibration is what I would think.
Mm-hmm. Yeah, that'd be something kind of take into account during that calibration. Question here about have you thought about condensing or compressing the 10-year rainfall record into shorter durations? I think you showed in the presentation on that last slide, you did a 3-year simulation.
Oh yeah.
It looks like, right? So it wasn't just the 10-year, but did you do a 1-year or 2-year, condense that at all anymore?
Yeah, no, that's right. So we did one big 10-year run, and it took like a week or something to run. It was pretty entertaining. Our BT group was like, "Why is this thing just running flat out for days? Like, what's going on?" I was like, we're just doing some modeling. No big
See
deal."
what happens, you know?
Yeah,
Maybe
see what happens. Yeah, I mean, why not? But when that started taking a while, we realized we got to do something different. So we broke it out into 3-year chunks, and that basically took about a day. So that was really kind of what happened. It was like, okay, well, what's the what's that breakout look like where we can get a model to run in a day? And so it was about 3 years. So we did end up having 3 separate simulations for 3 years or so each. That also made it a little bit easier because that one 10-year run, once it was done, it was about a terabyte of space. And so trying to load the model results into ICM was pretty tough. So the 3-year ones weren't too bad. You could drop that simulation in and it would kind of work through it in a reasonable amount of time, which is impressive to say the least. But the 10-year one, it was just a little bit too much.
I'm just imagining the sliding bar in the top, left corner of ICM, right? Dragging that around to the different time step. Like, I just want one day.
Yeah.
Very sensitive.
10 years of hourly data definitely added up quick.
Yeah, that's a lot. Very good. Well, yeah, lots of requests for that tips and tricks. So if you could help us out there, Stephen, since you've got that maybe a little handier. And then I do off my computer here. That'd be great, and I'll send that out to folks here, and we'll probably attach that to the recording. Stephen has generously agreed to, we'll leave this as an on-demand recording on the InfoWorks website there. So hopefully everybody will see a link to that, and probably with that link, we'll send out kind of the tips and tricks presentation for you all on those RTC controls there. All right. Any kind of final thoughts here, Stephen, as we may wait for maybe 1 or 2 questions to come in? Otherwise, we can certainly kind of let you off the hook a little early here, just shy of an hour. But any kind of final things for folks out there? I'd
say, ICM's definitely I don't know that you can do this kind of stuff very easily in some of the other software packages, like InfoSewer Pro or InfoSwim. You probably can to some degree with InfoSwim, but like Bob was saying, there's some challenges there. So ICM's definitely the software to use to do this kind of thing. I didn't really show all the use cases we've done, but we've used it to kind of help us hone in on lift station operations for influent lift stations at treatment plants and stuff. So I think our design teams have found a lot of value in just having this thing being able to run a varying flow pattern and provide some kind of just verification of what they're doing with a low effort, to do that. And you don't have to, a lot of those projects you might get into CFD modeling later, or potentially the scale model stuff. But early on, where you're just trying to understand, are you going the right way? a little ICM model can really provide, the good insights and make sure you feel good about what's happening.
Right, kind of, you're on your first slide, hitting that sweet spot between, just doing something in Excel versus the CFD modeling, a more intensive ICMs, kind of right in between those, able to be visual, but still simple and doable at the same time there. So,
and like that grit removal project, we went through the, full design of that facility, and then there was also a, I guess like 60% design or something. There was a scale model built to kind of just do it as a design verification and stuff. So it's definitely not a one or the other. You can kind of use them in tandem to help you work through the design process. So.
All right. Perfect there. Well, yeah, thank you everybody for joining. Again, we'll be back next week, same time, looking at fire flow and water distribution a little bit. But appreciate everybody's participation and questions. And thanks again, Stephen, for the presentation. There's our emails there if you need to get in touch further. All right. Have a good one, everybody.
You'll have a good one.